Chapter 3 Nuclear Energy 3.1 Nuclear Fission and Fusion. Nuclear fusion may provide a lot of energy compared with chemical energy. Nuclear fuel has a very high energy density. A spaceship powered by nuclear fusion can be relatively light and yet powerful. However, a fusion reactor is not yet developed. 1. Nuclear fission. There are over 400 fission reactors all over the world, including 2 at Daya Bay nuclear plant. When a heavy nucleus breaks into 2 or more nuclei, nuclear fission occurs and nuclear energy is released. For example, the fission reactors at Daya Bay uses uranium-235, which typically splits into 2 when a slow-moving neutron is absorbed. 2 fast fission neutrons are emitted in the fission along with the nuclear energy. So this is what nuclear fission looks like. A slow-moving neutron is absorbed by the nucleus in the middle, which splits into 2 with fast-moving fission neutrons emitted, along with the nuclear energy, in the form of kinetic energy of all these particles. And what if there are not only one, but many uranium nuclei? The fission of the first uranium nucleus will produce 2 fission neutrons, and these neutrons may then start the fission of another 2 uranium nuclei. And let's see what happened then. 1 to 2 to 4. And we call this chain reaction. A large amount of energy is released as there is a large number of fission reactions. It is interesting to find that nuclear energy comes from mass. Uranium-235 undergoes fission. The total mass of the product side is smaller, and the loss in mass becomes nuclear energy. Typically, the energy density of nuclear energy is 1,000,000 times that of chemical energy. 2. Chain reaction and critical mass. Fission of a uranium-235 nucleus is triggered by slow neutrons only. The fission neutrons are fast-moving, on the other hand, and so they have to be slowed down. If there are enough uranium-235 nearby, the fission neutrons may help to split other uranium-235 nuclei. The process continues, and a chain reaction of nuclear fission results. The mass of uranium-235 must be larger than a certain critical mass, so that the percentage of fission neutrons captured may sustain the chain reaction. In other words, when there are too little uranium-235, a lot of the fission neutrons may escape from the reaction core, and the chain reaction cannot occur. Example 1. Fission of plutonium. For part B, there must be at least 1 fission neutron for chain reaction to be possible. And now 2 fission neutrons are produced. And of course, the mass of the plutonium field must be larger than the critical mass for chain reaction to occur. 3. Nuclear fusion. In nuclear fusion, 2 small nuclei fuse together into 1, and nuclear energy is released as the product is more stable. The energy released by fusion per unit mass is about several times that by fission. Nevertheless, nuclear fusion is difficult to start. As all nuclei are positively charged, they must have very high kinetic energy to approach each other at high speed. So the temperature of the field must be extremely high. You should note that While the energy density of fusion is higher than that of fission, each fission reaction releases more energy than a fusion reaction. Hydrogen fusion occurs at the center of the Sun, which is the source of solar energy. Example 2. Fusion of nitrogen and hydrogen. Fusion of nitrogen and hydrogen is also possible. It also occurs at extremely high temperature. Do check point 1 below.